Okay, so in this video I'm going to talk about the insulated ends, the case where that the ends are going to be insulated of the bar. How we can solve our heat equation in this case. Okay, so suppose the bar has insulated ends. What is the meaning of this? Hence, no energy is lost across the ends. So if we have the bar here and we have the left and right end, there is no loss of energy on around this ends. The temperature distribution is modeled by initial boundary value problem. As we can see, this is the heat equation. This is valid for everything between 0 and L for X and for any time. Then we are going to say that the insulated ends, we have insulated ends means that partial U partial X at x equal to 0 at any time t should equal to 0, right? And also for the case of the right end, partial u partial x, the heat flow, at the right end at x equal to L at any time t, it should equal 0 also for any time t, right? This is the meaning of the insulated ends in a mathematical form. And after that, in between, what is the value at t equal to 0? What is the initial condition? We says that there might be a function here, which is, we call it f of x. So we're going to put it here as a function. We're going to put, or we say that u of x at time t equal to 0, the initial time, equal to f of x for x between 0 and L. For x between 0 and L with them included. Okay, so this is the meaning of the insulated ends boundary conditions in a mathematical form. So we need to solve our heat equation based on these boundary and initial conditions. We can solve it easily, and we are going to find that our equation, our solution, after some derivation, simple derivation, you can find it. You're going to find that u of x and t at any point x at any time t equal to half C node, which is seemingly to be a coefficient here, C node, plus the summation of many terms from n equal to 1 to infinity, Cn, another coefficient here. Okay, so this is when n equal to 0. This is when n equal to 1, 2, 3, and so on. Cosine n pi x over L times the exponential function e raised to the power minus n squared pi squared kt over L squared. Okay, so this is the solution. Okay, and at t equal to 0, initially at t equal to 0, our temperature ux at t equal to 0 equal to our function. That's right. This is what the insulated ends boundary condition is telling us, that inside the bar there is a function at time equal to 0. There is a function that it will start with, and it equals to half C node plus, so this is at t equal to 0 as I said, plus summation from n equal to 1 to infinity Cn cosine n pi x over L. Okay, so based on this we are going to choose, this is based on our initial conditions, so we are going to use this Cn is going to be like this. Okay, using Fourier cosine coefficients of the function f on the interval 0 to L. We have solved this many times before, okay, so you are familiar with what is the meaning of Fourier cosine coefficients. So in this part we are going to find that Cn equals to 2 over L, the integration from 0 to L, f of z cosine n pi z over L dz. Okay, now we have obtained everything. Remember well, this is our solution, this is our coefficient. Okay, so this is the two main things that you need to know in order to solve for the case of insulated. Okay, now let's jump directly to an example. Suppose the ends of the bar are insulated, now insulated, okay, and the left half, actually this is the bar here, we have like two halves. This is the left half, which is from here to here, of the bar is initially at constant temperature T. It seems that like constant temperature T here. Okay, A, not T. While the right half is initially at temperature 0. It is 0 here. Okay, so initially means that at T equal to what? 0. This is why he used here initially. Means that T equal to 0. And here initially also means that T equal to 0. The starting of our function at T equal to 0 is going to be something like this. Here this is A for the first half, and the second half it is 0. Right? So we're going to put it like this. This is the function that we have. F of x equals to A for x between 0 to L over 2, the first half. And after that equal to 0 for x between L over 2, starting from here to here, it is going to be 0. Okay, to L. Okay. Now we are going to compute for n equal to 0, C node. Okay, C node. We want it because, as you remember, we want this C node first, and then we're going to compute Cn after that. Okay, so C node equals to 2 over L. Do you remember? From the previous slide, it was 2 over L, the integration from 0 to L, f of z cosine n pi z over L dz. It is L here, right? Because we're talking about the entire bar, but we know that we are going to talk only about half of the bar, because the remaining half is going to be 0 always. We have f of z here. This is going to be 0 for the next half, so everything is going to vanish, right? So there is no integration. So here we are going to compute our C node for the case, or for the interval from 0 to L over 2. So it equals to 2 over L A, which is, this is the function f of exactly of z dz, right? Okay, so in this case we are going to have this is actually is going to have the constant that we mentioned before. The function here is going to have the constant. So let's go back here. So yes, this is the C node that we want to obtain, and based on our case, if we are going to have n equal to 0, right? So this is going to be cosine n equal to 0, so cosine 0. Okay, cosine 0, so it is going to be 1 at the end. So here C node equal to 2 over L, limited integration from 0 to L over 2 for the A, so it gives us A. And for the case of n equal to 1, 2, 3, which is any positive number, then Cn is going to equal 2 over L, the summation or the integration from 0 to L over 2. A cosine, actually A here, it is going to be like the function that we have. It is going to be the function that we have here. This is as if f of x here. Cosine n pi z, okay, dz. So it is, let's go back here, f of z cosine n pi z over L. Okay, so this one is going to be A. This part we're going to calculate it now. Okay, so now we have, this is A and this is cosine n pi z over L. This is the integration variable, and then we are going to rearrange it after the integration, limited integration, simple and easy for you. Then we're going to have 2a over n pi sine, because this was cosine, after integration it's going to be sine n pi over 2, n pi over 2. This means that our solution for the heat equation at any time t and at any point x along the bar is going to equal, this is a over 2, which is the part of exactly the C node. You remember? Okay, because here in our equation, if you remember, have C node. So already we have at the end C node equal to A, then the first is going to be half A node, and then the remaining is going to be the remaining part of the equation. It is going to be 2a over pi, the summation from n equal to 1 to infinity, 1 over n sine n pi over 2 cosine n pi x over L, and here it is going to be the exponential function containing n, k, t, and L. Okay, since sine n pi over 2 equal to 0, this is right, sine n pi over 2, it equals 0 always for if n is even, right? If n is even, always this term, sinusoidal function, is going to be 0. We can retain only odd n in this summation to write this solution as, you remember, as we have done in the previous video, we have retained only the odd values because the even values, they are going to be 0. So we remove this n here, or replace it, not remove it, let's say assume, replace it here also. They are going to be replaced by 2n minus 1 as we have done in the previous video. Okay, so that we are going to retain our odd values only in the summation and remove the even terms or the even values because it's going to be 0. So we have removed this n and put it 2n minus 1 here, 2n minus 1 here, and 2n minus 1 here. Okay, so this is our solution. Okay, this is our solution. It depends on what exactly? First of all, it depends on the number of terms that we are going to take. Okay, this is n. And number 2, it is going to depend on the x, the point where that we are calculating or evaluating the temperature. And number 3, we are having the variable t, which is the time, at which time that we are going to evaluate the temperature. And of course we have the constants. We have some constants here, which is going to be L. This is one constant, and there is another constant called K. This is another constant. So we have, these are constants that we are we know they are given, and these are going to be our variables. Okay, we can control them and we can change them. Okay. Okay, so this is the end of this. This is the end of this video. Thank you for listening, and see you in another video soon.